so here we have our second flux. This is the Godunov flux. I've already written out the expression to save a little bit of time. So again, we have a numerical flux indicated with a hat that we're going to evaluate only in terms of its normal components. We have here the definition of its normal component in the plus side. There's some element defined to be the plus element. And again, just to reiterate this, of course, the negative one, the one evaluated on the negative side, is then simply defined to be minus of fg dot n minus, right? So it's going to be defined to be equal and opposite. So that's going to already bake in this conservativity, right? That the jump is equal to 0. And our Godunov flux is going to be defined in two ways depending on which value of phi is larger. If phi plus is the smaller one, so in the drawing that I have right here, we might have a certain traveling wave or something like that, where we have a larger value here and a smaller value here. So then we're dealing with this case here. Then our Godunov flux is going to be equal to the minimal of f phi dot n plus. And if we deal with a traveling wave that looks opposite to that, so we have a larger value upwind, then our Godunov flux is going to be the maximum of f phi dot n plus. Okay, so let's try and evaluate that for the case of linear advection and see what kind of nicer expression we can get for that particular case. So now I'm going to again choose a certain element orientation relation. I'm not sure if I'll again show that you can also change the plus and minus sides and get the same expression. We'll see how far we get. But what's important right now as well is that we're going to have to choose between two cases. The case where we have a value larger in the upwind direction or a value larger in the downwind direction. So I'm going to start with, well, the top one here, so that would be that we have a larger value in the downwind direction. So something like this. So then phi plus is going to be smaller than phi minus. So in this case, the Godunov flux is going to be equal to, well, f phi dot n plus, so that's going to be a dot n plus times phi times the, times phi, where phi is going to be such that we get the minimal value. But we know that phi plus is going to be the smaller of the two, so naturally this is going to be equal to this. And okay, so that's going to be f hat g dot n plus. And of course f hat g dot n minus is going to be, well, opposite to that, or we get a dot n minus phi plus. Okay, good. So that's the first case. Let's consider the second case, where again I have plus and minus, but now my larger value for our concentration, for example, phi, is going to be in the upwind side. So now we have phi plus is larger than phi minus. And the advective vector is still going to be the same one. So what do we get now? Well, that's going to be the second case. So we again have a dot n plus times phi, but now phi is such that we have this expression being maximum. One thing I should actually point out here is that this one is positive, right, in our current orientation, as was this, and as was this. Oh, sorry, no, not that one. But the one that we're dealing with, the a dot n plus, is going to be positive. And that's why I could say before that the minimal here is going to be multiplied by the smallest value. If a dot n plus had been negative, then we would actually have to do that differently. And that's exactly why it's going to be independent of how we position our elements. You know what, I will show that actually in a second. So then we have a dot n plus times phi, but now such that we have the maximum expression of this. A dot n is positive. So the maximum expression is obtained for the maximum phi. Well, that's what we knew to be equal to phi plus. So again, f g dot n plus is going to be equal to that. And f g dot n minus is going to be equal to a dot n minus times phi plus. So what do we see? Well, in both cases, irrespective of which concentration is higher, the upwind or the downwind one, we get an expression in the form of f hat g dot n plus or minus is going to be equal to a dot n plus or minus times phi upwind. And that's also what we saw for the Leibniz flux. That's also what we wanted to be for the linear advective diffusion case. We get an upwind flux. Okay, so was that also true then if we flip the orientation of our elements? Let me just put that below this. I'm not even going to try and make this nice. So then we have minus and plus. Suppose that I still have the same advective vector. Of course, I could also make the same arguments flipping the advective vector, but I hope it's clear that it's going to be independent of what it's going to have the same result whether I'm flipping my elements or I'm flipping the advective vector. And let's start with, I'll only actually do the one that looks like this. So that was the first case here. So then we get a dot n plus. But now this is going to be a negative value. This is going to be smaller than 0. And again, we want to have the minimum of this now. But the minimum, if we have a multiplication with the negative sign, is actually the case where our phi is going to be as large as possible. Right, I'm getting into a conflict here. Give me 1 second to figure this out. Oh, yeah, sorry. Maybe you already saw this. If I consider this case, and because I flipped my elements, now I'm no longer dealing with the top case, I'm dealing with the bottom case now. Yeah, so in this case, phi minus is going to be smaller than phi plus. So I'm dealing with the bottom case here. Which means that I'll actually have to take the maximum of my flux evaluation for any kind of phi in between the values that we have on either side of the interface. And the maximum for, if I multiply with a factor that is negative, then the maximum is going to be the one that has the smallest value. So that's going to be equal to phi minus. Yeah, and again we see that the Godunov flux dotted with n plus is going to be equal to, well, that. And of course f g dot minus is going to be equal to a dot n minus phi minus. And again for this case we see that we have here the upwind value. And it's a straightforward extension that if we consider the case where phi minus is larger than phi plus, then we would again get the same expression with the upwind values here. Okay, so that's the second example of a numerical flux, and we pretty much get the same conclusion. Again, I should say, and I should emphasize, that we get the same conclusion for the linear advection problem. And that's the simplest case of a hyperbolic conservation law. Most interesting physical phenomena involve more complex cases for which these fluxes do not all coincide. And again, I'm asking you in the homework assignment to work that out for the Burgers equation. Okay, that's it for this video. And in the next video, I'm going to consider the Enquist-Oshir flux.